Okay, let's dive in.
Uh,
We're all sort of swimming in information these days, complex problems everywhere. Feel like we always need tools to simplify things.
that's so true. And sometimes the best tools aren't brand new. They're established mathematical ideas, like the one in these sources, logarithms.
Logarithms,
Right.
right. The material mentions their main job is making long, tricky calculations easier.
Exactly. That's the promise right at the start, making things easy.
Okay, easy sounds good. Where do we start? The source seems to link them straight away to exponents, something we might know a bit better.
Yeah, it does. That's the key relationship. It shows how exponential form and logarithmic form are connected. Take their main example. $34 equals $8104.
Right, 3 to the power of 4 is 81. Standard exponent stuff.
Precisely. Now, the logarithmic way to say that exact same thing is log 3 81 hobbers equals $4.
Log base 3 of 81 equals 4.
See how it flips? The exponential form gives you the result of raising the base, 3, to a new exponent 4. The log form asks, well, what exponent do you need on that base, 3, to get the result, 81?
Ah, okay, so it's asking for the exponent itself. The answer is 4 in both cases, just framed differently.
Exactly. Two sides in the same coin, like you said earlier, like we were thinking. The general definition locks this down. If you have numbers A, B, C, A can't be 1, and 1 can equals C day.
Then log of C equals B day.
That's it. They are fundamentally equivalent statements. 1, A, B, C, if and only if, log of C, A, D, O, B, P. You can just swap between them.
Like a translation. What was that quick example again, the one with the fraction or decimal?
Oh, yeah. $2 to 3 equal 0.1255. That's the exponential form base 2 exponent minus 3 result 0.125.
Okay.
So to translate that, you use the same parts. The logarithm uses the base, which is 2. It asks about the result, 0.125, and the answer is the exponent 83. So log base 2.125 is made as to 3. Log base 2 of 0.125 is knit as to 3.
Got it. I see the pattern. But, okay, how does knowing this definition make actual calculations easier? That was the original promise.
Right, good question. It's not just the definition itself, it's what comes from it. It's the properties of logarithms. These properties come directly from the rules we already know for exponents.
Okay, like what?
Well, the big one, especially historically, is how logs handle multiplication. The sources point towards this. The log of a product, say 6 times y, is actually the sum of their individual logs. So log x times y, log x plus log y, y.
Hold on. Multiplication turns into addition.
Yep.
How is adding easier than multiplying? I mean, today we just use a calculator.
But think before calculators. Imagine multiplying really large, awkward numbers by hand. Super slow, easy to make mistakes, but adding.
Right.
Much, much simpler.
Okay.
So people used log tables. Huge books of pre-calculated logarithms. If you needed to multiply, say, 1.23 by 4.56.
You wouldn't multiply them directly.
No, you'd look up log $1.23 Selma's in the table, look up log $4.56 town, add those two smaller numbers together, which is easy, and then use the table in reverse sort of to find which number had that sum as its logarithm.
Wow. Okay, that would be way easier for complex numbers back then. It actually transformed the operation.
Exactly. Turn multiplication into addition. Similarly, division became subtraction and taking powers became multiplication. These transformations were revolutionary for science, engineering, astronomy, anywhere with heavy calculation. That's how they simplified things.
That makes so much more sense now. It's not just abstract math. It was a practical computation tool.
It really was. So understanding that core link to exponents gives you the what. But these properties, these laws, they show you the why they were so powerful.
Okay, perfect. Let's wrap up this deep dive then.
Sounds good. So to boil it down from the sources, logarithms are this really clever way of looking at exponential relationships. And because of that connection, they have these properties.
Properties that let you change the math involved, like swapping multiplication for addition, making hard calculations, well, less hard.
Exactly. The main takeaway for you is really seeing that two-way street between exponents and logs, y of e's, CO2, means the same as log of c equals b there. And knowing that unlocks these powerful rules for simplifying work.
So it really was about changing the nature of the problem.
Which leads us to a final thought, something for you, the listener, to chew on. How does that very ability, the power to transform an operation like multiplication into something simpler like addition, how did that fundamentally change what becomes mathematically possible, or even just practical, to figure out what does that tell us about the power of just looking at a problem differently?